So in the last set of videos, we talked about confidence intervals. We had this idea of the big picture of statistics. We're using data to make a prediction or an estimate about the population. So confidence intervals gave us the ability to estimate a parameter, and specifically we were talking about P, the population proportion, with some level of confidence. We're going to look at an analogous procedure called hypothesis testing or significance tests. And we'll see in a little bit, we always agree our results from the confidence intervals and the hypothesis test are always in agreement with one another. Also, some good news, the last few weeks of class here, the only two procedures we're going to be doing are confidence intervals and hypothesis test or significance test. So I know this upcoming one has a whole lot of steps to it, but get these down well the first time and the rest of the semester is going to go very smoothly for you. All right, so significance test, we're going to be first talking about this in terms of proportions. Step 0, I call it step 0 because it's really important in practice. In this class, we're going to kind of gloss over it a little bit. But step 0 is just checking that our assumptions are met. And usually they're going to involve some kind of randomization and an appropriate sample size. So these should look familiar. They're the same assumptions we had for confidence intervals for one proportion. The first one is that our data come from a random sample. And this is to ensure that there's no bias. Our data truly represents the population. And then our second one has to deal with sample size. So if you recall, when we're talking about one proportion, that's our setting now, we're trying to make a claim, test a claim about the population proportion. We needed the number of successes to be at least 10 and the number of failures expected to also be at least 10. We needed this for normality, so if we have the same assumption again, you're kind of getting a little foreshadowing of what's to come. Normality will also play an important role in a little bit. So check our assumptions. Again, really important in practice. Sadly, we're just going to gloss over it a bit for now. Then our first step that we're really going to get into, that's going to be the meat of the process here, is stating our hypotheses. Okay, so I'll be looking for you to state the hypotheses. You always need to state both of these things, two hypotheses. The first one, HO or H naught, is our null hypothesis. You always write that one down first, and you can think of this as our initial assumption. We're going to write down something we're going to assume is true through all of our calculations and see if we can prove otherwise. So H naught, think initial assumption. Then HA, the alternative hypothesis, this is where our research claim goes. So HA, you can think of as our research hypothesis. This is the thing we're trying to prove. So let's jump right into an example to help this make more sense. So I don't know if anybody's a fan of Stranger Things. I think I asked that once in class, and quite a few of you were. If you're not, or if you have never seen it, there's something to do while you're homebound now. So anyway, Stranger Things, there give some just general information about the show. And we have some questions here at the end talking about that adult audience, the 18 to 49 age range. And our research question here is, do we have evidence that more than 11% of adults in this age range watch this show? Maybe you're like me and you absolutely love the show and you want to see, do in fact more than 11% watch this show. Okay, so let's practice writing our hypotheses. We're going to do this for our particular problem here, and then I'll show a couple other variations of what you might see. So I'm going to write HO and HA because we already mentioned you always need both hypotheses. They serve different roles. Let's start with the easier one, HA. This is our research question. We just highlighted our research question. Can we show that more than 11% of adults watch the show. So we're talking 11% of proportion. We're in the context of proportions. And my question is not for my sample, it's for the whole population. So if you remember, P was our symbol for the proportion for the whole population. So my research question is this: is the proportion of the entire population that watches the show in fact greater than 11%? Since we're writing it as proportions, I'll write it as 0.11. So that's my research question. Is P, the proportion, more than 11%? HO, my initial assumption, is always going to have this statement of equal to in it. I need something to start off assuming. So we're talking about proportions. I'm going to use P in both of these. My question is, is it more than 11%? I'm going to start off assuming that it is in fact just 11%. The proportion is 11, and then I'm going to try and prove that it's in fact more than 11%. So that goes with our research question up here. We could have some other variations. So for example, maybe the question said, maybe you're not a fan of the show, you can't understand why people would like it, and you think, man, less than 11% watch this show, it's not that great. So your research question would look like this: P is less than 11%, if that was your research question. Again, research question goes in HA. Our null hypothesis is going to be the same though. We're going to start off assuming it's 11% and see if we can show, in fact, that it's less than 11%. These two variations have a specific name. They're often called one-tailed test. And the reason one-tailed test or one-sided test, because our research question has one specific direction, specifically greater than, this case, less than. So one-tailed test because I have one specific direction my research question is in. Another variation would be, maybe I don't know if it's greater than 11% or less than 11%. I just think my teacher's being weird and using 11% because that's the main character's name. So I think it's just different than 11%. I have no idea what it is, but it's not 11%. So P is not equal to 0.11. And then HO, though, is still going to be the same thing. We're going to start off assuming it is 11 and then see if we can show otherwise. This variation is called a two-tailed test. And the names will make even more sense later on. But two-tailed tests, and you can see the difference here. Two-tailed because of the not equal to. Could be less than 11, could be greater than 11. I'm allowing for both options or two different options. I just don't know what it is. Okay, so that's an example of our hypotheses. Let's look at just a comment or two when writing these about common mistakes here. So first thing, make sure you always use parameters. We're making a claim about the entire population, not the data. Okay, so always use parameters. So in this case, we're talking about P, the population proportion. Later on, we might talk about the mean of a whole population. That symbol was mu. So use the parameters notation because we want to make a claim about everybody. Never use notation of statistics in your hypotheses. Never use, sorry about the handwriting, statistics. And for example, X bar would be the mean of the data, or P hat would be the proportion of the data. Don't use that notation. We're not making a claim about the data. We're making a claim about the entire population. Okay, and then notice that HO always has an equal to sign in it in those variations. And then notice HO and HA both have the same number, and specifically that number came from the research question, not any data in the problem. Same number in HO and HA, and it's from the research hypothesis. Oh, sorry, handwriting's getting a little messy here. Research claim, that's shorter to write. Not from the data. Okay. All right, so no, I haven't even collected any data at this point. I'm just stating a question, no data involved. All right, step 2 is where the data is going to come into play. So in this step, we're going to calculate our test statistic. And our test statistic is going to measure how far off our data is, or the point estimate, from our initial assumption, or HO. So I'm going to write this out in general first. So we're going to check out our point estimate. Again, this represents the evidence we've collected, the data we have. We're going to see how far it is from the null, our initial assumption. So is it measuring that discrepancy between data and initial assumption? And then we need to scale this. We're going to scale it by the variability that we expect to see. Okay? A difference of 10 is not so big on a scale of millions. A difference of 10 is huge on a scale from 0 to 20. So we need to scale that by our standard error. So measuring that discrepancy between data and initial claim, initial hypothesis. This setup should look really familiar to something you've been using. And if you're thinking z-score, you're exactly right. This guy is just the z-score. Again, which is why the normal distribution is going to be really important in this section as well. So this was our formula for general. I mentioned we're going to be doing this the rest of the semester. So get ready to see this formula in several contexts. And let's look at it specifically for a test, a hypothesis test, or a claim about a single proportion. All right, so we've mentioned it's a z-score, so I'm going to call this z-calc. Calc is just kind of arbitrary to say, hey, I'm calculating this thing for a hypothesis test. And if I'm talking about p, the population proportion, then my point estimate is p hat. So point estimate for population proportion is p hat. I'm going to see how far it is from my null hypothesis or initial claim. So I'm going to call this guy p naught. That's my number in my initial claim. So on the previous slide here, my p naught would be 0.11 or 11%. I'm starting off assuming it's 11%. And then I need to standardize this by the standard error. So if you remember the formula for standard error for proportions, it's that p 1 minus p all over n, and everything, including the n under the square root. The p that we're using down here is associated also with that initial claim. So I'm going to make sure to write that as p naught in the denominator. Be very careful about that. All right, so let's try this out for our particular example. Suppose I asked you guys, everybody in the class, do you watch Stranger Things? And since we're doing this distance, I'm going to pretend I asked you, and I got that 10 out of 30 of you say you watched the show Stranger Things. We only have 29 people in the class, so I'm the 30th answering yes, I watch it. All right, so this guy would be my data or my evidence. That's my p hat that I've calculated. So about 33%. Remember, we're going to be rounding everything to 4 places to keep things consistent. So to calculate our test statistic, I'm going to call this guy z-calc. You have the formula up above to remind yourself here. So the data or the evidence that we collected is 0.33 repeating. I'm going to see how far is my data from the null hypothesis. So we looked a moment ago on the previous page, H naught, the null hypothesis, our initial assumption is that 11% watch this show. And then our standard error, we're going to be real careful down here. The P we're using is P naught, the value from the null hypothesis. So 0.11, 1 minus 0.11, all over our sample size of 30 students plus 1 teacher. And if you work that out, make sure you're careful with your order of operations here, you should get 3.9089. All right, you guys have a history with z-scores. You have some intuition about this. This is telling me my data is almost 4 standard deviations away from the assumption, or a z-score of almost 4. Big z-score or not so big? Hopefully you're saying out loud to yourself, big z-score. So this is telling me that's like an outlier. If the null's true, my data is an extreme outlier. So this is a big z-score, and this is telling me data is far, really far, from my initial assumption. Okay. So kind of tuck that thought away for later, but that's basically saying the data doesn't match up with the initial assumption. HO's probably not true. Okay. All right, so that wraps up this first section for hypothesis testing for one proportion. We'll continue on with the last 3 steps of the process in the next video.